Arakawa, and I are co-supervising the group. And our research fields and the members' backgrounds are broadly ranging from electronics to mechanics to chemistry. And our aim is to develop advanced sensor technologies for healthcare, biomedical and health science. And through these four research activities, the captive sensors, biochemical gas sensors, immunosensors, and organic engine. So in the next 3 slides, I'm going to talk about captive sensors and the biochemical gas sensors, and with the rest of the slides, I'm going to talk about immunosensors. So this is the concept of captive sensors. So the conventional medical and healthcare devices like implantable and wearable devices have gained a lot of popularity for the last decades. However, I'd like to point out some drawbacks in these devices, which are, for instance, implantable device. It's implanted, of course, in invasive way, and it contains the infection risk. And wearable devices is still used as merely as an activity measure and not for medical use. So to advance these technologies to a level that allows us to measure physiological parameters, we have been proposing captive sensors, which are attached on the body cavities. And conjunctival sac with tear glucose sensor, and oral cavity with mouth guard type sensors. And this is one of the example, or this is one of the application field of captive sensors, which are evaluation of blood glucose level. So as Professor Matsumoto talked about, already introduced, the diabetes is a global issue. And about 400 million people have been suffering from diabetes. And conventional methods like blood glucose meter is an invasive method. You need to take a drop of blood from your finger, for instance, and of course it's painful. Well, less painful these days, but it's still painful. And the data is discrete, so you cannot actually trace the fluctuation of the blood glucose level. So when you look for other body fluids which contain glucose instead of blood, they are tear or saliva. So for instance, tear contains 1/20 of glucose compared to blood glucose, and saliva contains 100. And for tear glucose, we have developed a soft contact lens biosensor. The electrodes are fabricated on contact lens and use the enzyme to measure tear glucose. And this is an experimental result through OGTT with the rabbit. So we attach this contact lens on the eyes of on the rabbit's eye, and it was we could successfully measure continuously measure the tear glucose level, which has the same trend with the blood glucose level. And for saliva glucose, we have developed a mouth guard glucose sensor, and the electrodes and the data transmitter were integrated in the mouth guard. And as this picture shows, you don't easily realize that the sensor is attached on his mouth from the front view. So it provides us not only the capability of continuous measurement, but also comfortability and good cosmetic appearance, and which are definitely important to gain the popularity in the market. And next is a biochemical gas sensor and an imaging system. So for simple evaluation and metabolism and disease screening. And some volatile organic compounds known to be related to disease or metabolism. And for instance, acetone is known to be related to diabetes. And if it is possible to measure these VOCs, volatile compounds, in your breath or skin gas, you can develop a kind of way to evaluate your physiological condition non-invasively and simply and rapidly. So to achieve this objective, we have developed a biosensor, that is a biochemical gas sensor. And it's a fluorometric biosensor using NADH fluorescence property. So by this biosniffer, we successfully measured the acetone with acetone vapor continuously. And as well as biosniffer, we have also developed a gas imaging system, which we call it SNIF-CAM. So this provides us spatial temporal information of human volatiles. For instance, please look at this picture. This picture is showing the acetaldehyde, gaseous acetaldehyde released from a pump. So as you see from this picture, the concentration distribution is not homogeneous. Actually, it's inhomogeneous. So if you study how the distribution is also related to the disease of metabolisms, it provides us a new knowledge in the medicine. So, so from this slide, I'm going to talk about immunosensors for healthcare and medicine, and especially by introducing a work for allergen monitoring. So the number of allergy patients have been increasing, and now about 1/3 of people have suffered from allergic symptoms. And one of the causes of allergy is the house dust mite allergens, and especially this protein called DELA-F1 from this mite shows a strong allergenicities. And unfortunately, it widely exists in residential or occupational indoor environments, maybe in this room as well. So, because of this danger, the WHO, the World Health Organization, has set certain standards. And the main routes of uptake of these allergens are inhalation or skin contact to airborne allergens, which are floating in the air. So a system which allows to monitor allergen concentration could be used to prevent from being exposed to those allergens. So as a result, it can be used for prevention of allergic disease. So there are still some challenges for the monitoring system, because in the monitoring system, the allergens must be rapidly and repeatedly measured via immunoassay. However, the conventional immunoassays, for instance, ELISA, of course, it shows a very high sensitivity, so it's very useful. However, you need a complicated and long procedure until you obtain result. And it is endpoint assay, so you can use this assay only for a single measurement. So these characteristics make these assays unsuitable to the monitoring system. So we believe that the characteristics of the promising sensors for the monitoring system are it allows short measurement time and repeated use, and plus advantage of ELISA. So to achieve or to develop these sensors, our objectives in this study are to develop an immunosensor for the monitoring system and measure the DELA-F1 semi-continuously. Semi-continuously means rapid and repetitive. So for the development of such an immunosensor, in this study, we combined a surface acoustic wave device and aura protein. And in surface acoustic wave device, it is composed of a sensing area here. It is called delay line, and input and output electrode, and the reflector. It shows the capability of label-free measurement of molecular binding events on this delay line, and provides us the possibility of easy surface modification. So